Okay, so this session we're going to be looking at fabric heat loss, and in particular we're going to be looking at U value, which is going to be one of the calculations you'll do with Josh Hobday in his mathematics session, which should be of a merit level. So what we need to understand, we've looked at various basic principles with conductivity, convection, radiation. It's still the same. Fabric heat loss is all governed by those physical principles. So let's see how we take that a little bit further and understand how we calculate the issues or design any problems out with fabric heat loss. So I've got a question for you. How many Nando's chicken wings are passing through your living room walls each day? Yes, chicken wings. So I bet you're wondering, what am I going on about? Chicken wings, I thought I signed up to a construction course, and my man's asking me how many chicken wings are going to go through my living room walls each day. Now, the reason I'm asking this question is that quite often when we look at calculations and formulae in engineering, the calculations, when you look at the formulas, they don't really mean anything. It's all theory, and they're just a set of letters and numbers, and we learn how to use those letters and numbers, and we make the calculation, and we derive at an answer, and we get it correct or incorrect, whatever, but it never really means anything. Okay, so what I'm going to do is we're going to go through that process where we understand about the formula, how it works. But at the end of this, when you calculate it, you'll convert the energy lost through the walls of your living room, and then you can convert it into how many chicken wings or milkshakes or fries or whatever. Personally, I'm a vegetarian, so I don't really care about hot wings. I don't really care about them at all. Now, if you ask me how many courgettes, how many cabbages and cauliflowers are going through my walls, now you got my attention. Okay. Anyway, without ado, let's take a look. So remind ourselves then, fabric heat loss, you'll recognize that image on the right. Obviously in the previous session we covered this, and certainly one of the key headline figures involved with that was this one, 35% loss through the walls. Okay, and that's what we're going to calculate U value on today, is through one of those walls, through one of your living room walls. So heat loss is a measure of the total transfer of heat through the fabric of a building from inside to the outside. Now, it's not always that way. Do you remember why? That's right, because heat always travels to the cooler point. So whilst it's true to say that energy in the form of heat travels from the inside to the outside, that's only true if it's colder outside. Obviously, if it's warmer outside than in, then the reverse is true. Okay, so it's either from conduction, convection, radiation, or any combination of these, and generally it's always as a result of the three, but it can be just one or two. Okay. So what is a U value? All right, so the U value is the measure of the overall rate of heat transferred by all mechanisms under standard conditions through a particular section of construction. So let me explain how this works. So the U value here, U value is going to be the total value of resistance, or what we say resistivity, to energy or heat. Let's just use the term heat. Okay, how much heat we're losing through the wall. That's U value. Now what we're looking at here is the formula itself, and it looks a bit, well, what is it? Okay, we need to break these down a little bit further and look at SI and SO, surface inside resistance and surface outside resistance. Now we'll take a little closer look at what those two mean, but what these two do is they sandwich the calculation. So in the center you have this here, which is the main body. It's the main body. So we've got 1 over RT. And this is called reciprocate. Okay, so it's the reciprocation. Let me just write this down. Reciprocate. Okay, so 1 divided by RT. So the RT is resistance and thickness. The R is the resistivity, T is the thickness. Okay, so typically we could have, let's suppose there's 4 materials in a wall. We could say that there's a plaster coating, there's plasterboard, there's a timber stud, and then there's a brick wall. Let's just say there's 4 of those. So what this would look like is as follows, and I'm going to write it out just at the top here. Okay, so it would be surface inside resistance plus, so you'd have the first one, so you'd have the thickness divided by the resistivity plus thickness divided by resistivity, third material and the fourth material. There we go. And then the outside resistance. Okay, and then all of this is reciprocated by 1. So let's suppose that this all equaled, I don't know, let's say 0. Let's scrap that. Let's say equaled 4.6 watts per meter squared Kelvin, and I'll explain what that means in a second. What we do is we take 1, we reciprocate 1 divided by the answer, which would be 4.6 watts per meter squared Kelvin, which equals, now I'm just guessing this, I'm just giving you a bit of an example. Let's say the answer is 0.26. In fact, this is incorrect here. We wouldn't put that there. We'd just say 4.6, and then the answer, once this has been reciprocated, would be 0.26 watts per meter squared Kelvin. Okay, so let's break it down a little bit further. Let's make it a little bit more easy to understand. All right. First of all, what do the building regs say? So the building regulations that cover this U value is the approved document L1A, and that's the Conservation of Fuel and Power in New Dwellings, 2013 edition with 2016 amendments. So that's the very latest one. Now, what you can see over here on the right hand side, obviously, is we're going to look at a wall. Okay, I don't know why it's done that. Let's go back a minute. Let's get my pen, and let's hopefully this plays ball. So we're looking at a wall, and the building regs state that the maximum permissible allowance for energy in the form of watts is 0.3 watts per square meter Kelvin. So for every square meter in your wall, in every wall, or and now obviously the roof, you can see that's different. Party wall is different. A swimming pool basin is different. But in the building regs, it gives you all the differing elements of a structure. A wall is an element, a roof is an element, a floor is an element, so on and so forth. So we're going to look at a wall today, and we know that if we calculate a wall with all its different parts to the wall, it needs to be less than 0.3 watts, otherwise it won't conform to building regulations and it won't pass. So this is why we need to design with heat transfer in mind before we even put a shovel in the ground and start digging to put the foundations in and build a structure, blah, 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 blah. There's no point in calculating it once the wall's in and then we find out it's exceeded that value, because it won't get passed by the building inspectors, and then we're in big trouble. Okay, very big trouble. So looking at this on the left hand side, so what we say is we're looking at this here. We're looking at this here. You can see the structure of a house, the shape of a house. Okay, and in that house you can see there's the wall. Colour it in a bit more. Okay, just there, and we can see 0.13, 0.04, their surface inside and outside resistances, and we can see here surface resistances. What surface resistances actually are is it's actually an air resistance due to convection currents at the surface. So if you look over here, on the inside of your wall, you see all these little tiny red molecules that stuck to the surface of the bricks. And then you can also see on the outside there is also I mean, you can't see this, you can't touch it, but every single surface of every material, of every object, has this convection current around it. It's almost like a static layer. But when you do the calculation, so if we go back to here, when we do the calculation, we always, let me get my highlighter, we always include surface inside resistance and surface outside resistance, because they have a value there. So that's part of the calculation. 0.04 for outside, surface outside, and surface inside 0.13. Okay, they're a standard. They're constant. They always remain like that. Now, also note that you'll see in the sketch here, if I can just get my little highlighter here, you can see that the values actually change depending on, like this roof here, which is a pent roof or a pitched roof. You can see that it's 0.1. Okay, you can see that the horizontal surface there, 0.17 downward. You can see the point is, you must always refer to the building regs to see whether or not you're dealing with a vertical wall, horizontal wall, so on and so forth. But these in general are the values. Certainly 0.13 inside for a wall, and 0.04 outside resistance. So for those of you who understand Kelvin, the absolute, so, or should we say absolute freezing equals minus 273 Kelvin, or 0 degrees in centigrade. Okay, but this is not about absolute, this is about magnitude. And when we refer to thermal units like heat units, Fahrenheit, Celsius, centigrade, Kelvin, etc., they're all the same. They're all, obviously you need to convert. You need to times 1.8, add 32 to convert Fahrenheit to Celsius, so on and so forth. But generally, if we say it's 3 degrees Celsius, it's 3 degrees Kelvin. It's the same. Okay, and that's why we've got this scenario here where it says watts per meter squared Kelvin. Okay, so I just want to point that out. So the example could be a concrete block having a resistivity value of 0.18 watts per meter Kelvin. That's to say that for every square meter of your wall, every square meter, it's 0.18 watts, which will be travelling through that wall, if the wall was just made of concrete block, every second. Something to remember, or something to, if you didn't know this, let's get rid of this, something about the nature of watts. So a joule, let me write this down, joule is a unit of energy, equals energy. But once you apply motion to it, so we're talking about heat travelling, joules per second, so we're timing how fast the energy travels through, so it's joules per second, which equals watts. Hence, again here, how many watts, so it's joules, units of joules of energy that is in movement, so that's why it's per second, which equals watts. So the block is saying for every single second, for every square meter, 0.18 watts, brackets, joules per second, will be travelling through. So all materials are divided by 1,000, so a 100 millimeter concrete block would be converted to 0.100. So that's T, that's the thickness. Okay, that's that thickness there. So this here, 0.18 watts is the resistivity. You can see it there, and obviously the thickness is there. Okay, the reason why it's divided by 1,000, it's an industry it's an industry standard. All materials are divided by 1000. Okay. If you're not happy with that, go and see the manager. Don't come to me. But if you're given a concrete block 100 mil, it is now 0.1. You just move everything 3 places to the right. Okay, and that's, you don't need a calculator. Just move everything 3 places to the right. Okay, so this is the worked example here then. So we've got the surface inside resistance, as we know, that's a convection current. It's a standard, never changes. Surface outside, so we've got 0.13 there, divided by the thickness of the material, the concrete block. That's a tick, because we know it's 0.100, because 100 mil divided by 1000 is 0.100. The resistivity, well, we got the resistivity from the manufacturer's stated detail, like on roll of insulation. You'll see the R value and the U value for that particular material. For blocks, for bricks, for tin, everything has a standard industry connected to it. Not all concrete blocks are the same. Not all insulation is the same. When you see 0.18 here, it doesn't mean to say that every time you see a concrete block, the resistivity is 0.18. Don't do that. It's not true. It's not correct. Every block has its own. Okay. So we've got the 0.13 plus 0.100 divided by 0.18 plus 0.04, which equals 0.725. Just do that with the calculator with me, so you've got that bit right. Okay. If it's not correct, if it's not 0.725, go back and do it again. Just make sure you're not making an error on the input of your calculator. So U, the U value, is equal to the reciprocation of 1 here divided by R. All right. So that is equal to, let me change the color of this. Okay. So it's, this here is the answer to our equation. So 1 divided by 0.725 equals 1.38 watts per meter squared Kelvin. Let me ask you a question. Does that conform to Part L of the building regulations or not? Can you remember? For those of you who said yes, you're wrong. So you need to refer back to a little bit earlier in the video when I was covering the building regulations. But the building regulations state, let me change the color of my pen. Let's do it in a green. States 0.3 watts per meter squared Kelvin per degree difference. In other, what that means is, so here we can say 1.38, that's way over 0.3. It's about 4.5 times, way too big. So that's why we don't build houses with just concrete blocks. We have to add more materials to try and stem the flow of heat energy passing through. So 0.3 watts, and it's per degree difference. So this is 0.3 watts. So for every square meter, no more than 0.3 watts is allowed to pass through that square meter of wall per degree difference. So if it's 20 degrees inside and it's 19 degrees outside, it'll be 0.3 times the temperature difference. So delta T, okay, let me draw that a little bit better. I don't want anyone getting confused what delta T is. Okay, let me get my pen again. Delta is a triangle. Delta T. Whenever you see delta, it just means difference. That's what the triangle means. Difference, delta, difference. That's it. So in this instance, it's delta T, the difference in temperature. So inside is 20 minus 19 outside equals 1 degree. So it would be 0.3 watts per meter squared per degree difference. In this case, it's 1. So so you can just multiply all the square meterage of the wall by 0.3. Because it's 1. If it was 2, it would be 0.6. If it was 3, 0.9, and so on and so forth. Okay, so about that Nando's then. How are we going to calculate it? Well, before we do that, I want to show you another worked example of a collection of building materials that make up an element. So we're going to use multiple examples of materials or resistance values, and then we'll come back and we'll answer that question. Okay, so the way we're going to do this is we're going to start off with a black pen is what we're going to do, and we're going to say surface outside. We're going to say a clay brick. We're going to have some glass wool, which is insulation. We're going to have concrete block, our mate concrete block. And you can see I've used the standard, well, I've used 0.18, which is the example we've just used, but as I say, it doesn't have to be, it's not always 0.18, so be careful with that. We're going to have plaster, and then we're going to have surface inside resistance. So what that would look like let's just do thickness in meters, and then we're going to do resistivity value in watts per meter Kelvin, and then we're going to do the answers on the side here. So so what that would look like is effectively we would have our wall, we would have say we'd have clay brick there, and then we're going to have some glass wool. Look at that, wonderful, wonderful. Who wouldn't want that in their house? Right, so then we're going to have concrete block, big sturdy concrete block. Wonderful artwork, look at this, beautiful. And then we're going to have some plaster. For this we're going to have some green plaster. Why not? Green plaster. And then what are we going to add? Okay, of course we are. So on the outside, there's our little convection current, our surface outside resistance. Very, very nice, nice, nice. And then on the inside, we're going to have lots of nice red bubbles and stuff for our inside. Okay, so that's a visual cross-section through the wall that's demonstrated on the left-hand side there. We don't need to name them, we can see what they are. This is obviously, let's say, outside, which equals 0.04, and then inside, which is 0.13. Okay, so moving over then, the clay brick, we're going to say that it's 105 mil, and we divide it by 1,000, so we're going to say it's 0.105 because it's in meters. Look, there we go, meters. The resistivity value for that, we're going to say 0.17. Okay, glass wool, we're going to have 100 mil thick insulation, and then that's 0.035, and you can see that 0.035. That's real. You can see the insulation it's got a very, very low number. So the lower the number, the more resistant it is in comparison to clay brick. The concrete block 0.100, and the resistivity to that was 0.18. And then we've got plaster at 0.013, so 13 mil. This is equivalent to 13 millimeters divided by 1,000 because it's meters there, and that has a resistivity value of 0.16. So we've got our over here, let's say the call it totals. So surface outside resistance, if you remember, was 0.04. Then we can say that the surface inside is 0.13. Then we say clay brick, when we divide the thickness by the resistivity. Remember, SI plus thickness divided by resistivity plus SO. That's what we're doing here. In fact, I've done this the wrong way. I've done it that way. It doesn't matter which way you arrange, but it it just doesn't matter at all. But so clay brick thickness divided by resistivity is 0.15. Then the glass wool is 2.85. That's a big one, isn't it? That's a big number. Concrete block 0.55. And then the plaster 0.08. We add all of those up and it comes to 4.16. Okay, 0.16. So what we need to do now is reciprocate that, so it's 1 divided by this answer here, all of these totals, okay, which is 4.16, and when you divide those two together you get 0.24. 0.24 what? What's missing? Of course, the watts. So it's 0.24 watts per meter squared Kelvin. All right, and let's highlight that answer there. Look at that. That's the answer. Now, the question, does that conform to building regulation? Yes, of course it does, because the building regs, Part L states 0.3 watts per meter squared Kelvin. That's where it states. So 0.24 is under that, so that's permissible. That's no problem. So of course the next thing to do would be to calculate the difference, obviously delta T, in terms of the inside temperature versus the outside temperature. Okay. So about that Nando's then. So this is where we use our newfound knowledge in calculating how many wings are going through the wall. So we're just going to look at one wall. Let's suppose that you live in a terraced house and your living room only has one exterior wall, which is your front room wall, the wall that looks out onto the street, okay, because the walls to the side of you are not external because you've got a house either side, and then the wall behind you would be a wall that's probably dividing the dining room or the kitchen, so on and so forth. Okay, so let's just bear that in mind. I'm just going to come back to that shortly. Right, let's calculate this. If we say then, if we take the answer of 0.24 watts per meter squared Kelvin per degree difference, let's suppose in that temp is equal to delta 2 degrees. So there's a temperature difference of 2 degrees. Okay. So we've got 0.24 watts per meter squared times delta T equals 0.48. Okay. And let's suppose in that your living room wall is perhaps around, usually it's 2.4 meters is usually the standard. Let's say 2.5 meters times 7, or that. I'll tell you what, let's just call it 15 square meters. So the wall equals 15 meters squared. Okay. Hope you follow me so far. So the 0.24 was taken from the previous example we just done, that worked example. So for every square meter, it's 0.24 times delta T, which is difference in temperature. So there's a 2 degree difference. That's what we got here. So it's 0.24 here times delta T, which equals 0.48. So 0.48 watts per meter squared Kelvin. We don't have to add the per degree difference because we factored that in with the delta T. It was 2 degrees. So what does that equal then? Well, we need to look at obviously 0.48 multiplied by 15. Obviously the wall space here, the amount of meterage. So it's 0.48 multiplied by 15, because that's how many square meters you've got. Don't forget, it's 0.48 watts per square meter. Okay, so there's 15 square meters involved with this, and that equals 7.2 watts meter squared Kelvin. Okay, and that is per second. Remember, joules per second. So for every second we're losing 7.2 watts. Okay, that's across the entire wall surface of 15 square meters. So 7.2 per second, and there's 60 seconds a minute, so it means we're losing 432 watts per minute. And then per hour it's 25,920 watts per hour. Now we divide that by 1,000, and I'll tell you why. Because a lot of you probably haven't seen an electricity bill, but your poor parents have. I certainly have. And what it's based on, if we say electricity is based on, well, it's measured in kilowatt hours. So kilowatt hours equals, on my tariff, how much I pay. So for 15.5 pence. Does that look like a 5? It looks like a 5, doesn't it? Let's scrub that out. Kilowatt hours equals 15.5p. So a kilowatt is 1,000 watts. That's what the K is for. Kilowatt. Kilowatt equals 1,000 watts. Okay. And we've got 25,920, so we divide that figure by 1,000. That's why we've got divide by 1,000. So that gives us 25.92 kilowatt hours. That's how much we're losing. A kilowatt hour is 1,000 watt. How many? So if you had a kettle that was, if you left the kettle on, that was 1 kilowatt. Okay, so you needed 1,000 watts to run the kettle, and you left that kettle boiling for 1 hour. That would be the equivalent to 1 kilowatt hour. So you're using 1,000 watts in 1 hour. Okay, so we're using, in an hour, we're using 25,000 watts, aren't we? Here, 25,920. Now, 25.92 kilowatts, and a kilowatt hour is 15.5p. So it's simply 25.92 multiplied by 15.5 pence, because that's what the modern, that is what the electricity people are charging today, and that is equal to £4.01. There we go. How many chicken wings can you buy at Nando's for £4.01? I don't know. I absolutely don't care. I'm a vegetarian. So what? I'm a rule breaker. £4.01. Now that's every hour. Now, something you need to remember about this figure here. Yes, that's a really high figure, and if you multiply that up, that's over £100 a day, and that's just ridiculous, isn't it? But we need to look at certain factors where these figures come in. We need to be realistic. Is that if you look at these, what you're seeing here is the statistics for the average temperatures per month across the year, and we can see that it's current and it's relevant. 2020, we can see obviously this bar here, this one here, is where 2020 stops. So obviously the because it's this color here, so we can say that these statistics are true up to May of 2020. All right, but you can see that they follow a similar pattern, and we can see that the average temperature here, we could take the mean average of all of these here, and so we were looking at around about 18 degrees there. We're looking as low as about 15. So that if we say 17 degrees is the mean average, in June, okay, well, on our example, we said delta T of 2 degrees. So we said inside the house 20 degrees, outside 18. So heat was going to travel to the cooler point. And we said that, well, it's £4 an hour, or however many chicken wings you can buy at Nando's an hour. But effective, what you need to realise is that, I mean, we can take extremes here where it's averaging around 5 degrees and it'll be 20 degrees in your house. So that's delta T 15. I mean, if we run the figures on that, it'd be like absolutely horrendous, wouldn't it? But this is it. This is what happens at winter when you have to when you have to insulate your home so well, because otherwise, if you don't insulate well enough, you really are going to get some massive heating bills and so on and so forth. And that's why your parents will be going nuts. And hopefully now you understand while your parents are proper giving out to you every minute of the day through the winter saying, would you shut that door, would you do this, would you do that, and you think, nag, 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 nag. Well, it's actually, when you start looking at this, you can see why. Now, it's conversely, when you get to, obviously we've had some really hot weather lately where it's gone into the 30s, mid 30s in some instances, where this whole thing changes, where you're actually not spending, no heat is being lost from your home because all the heat is coming in because of conduction, convection, radiation. So it's a bit of swings and roundabouts. So when we look at £4 an hour coming out your wall, let's take that with a pinch of salt, because when you have to take into account lots of different factors: climatic temperatures outside, the conditions inside, the fabric of the wall, what type of insulation you're using, what type of heating you're using, how much ventilation, how much accidental ventilation you've got going on the house with the stack effect, with drafts and so on and so forth. So please take the £4 an hour as a bit of a pinch of salt. It's only a bit of a light-hearted exercise, but at least it makes the formula a little bit more tangible now, doesn't it? At least it kind of means something. So have a think about this when you next have a conversation with your parents about bills, and understand that, although we can't see the energy being lost through the walls, it certainly is being lost through the walls, but not every day through the year, as this graph says. Okay. So that just leaves me to, oh, by the way, Josh Hobday will be picking up a merit calculation with this. Okay, so practice this session, watch it a couple of times if you can. Prepare yourself properly, familiarise yourself with all the letters and numbers and so on and so forth. Any questions, just ask, let me know, or Josh, no problem. And just to finish off by saying, answer the question, give the question back.